presenting optical compass today. Uh, okay, so the problem statement was that the bees had to locate them. That the bees they locate themselves in space using their eye sensitivity to light polarization, and then we had to design an inexpensive compass using polarization effects to obtain the best accuracy. And we also had to predict what would happen in the presence of clouds and how would it affect our accuracy. So interpretation was of the problem was that we had to use polarization of the sky, just like bees use polarization of the sky to locate the sun, and we had to use the sun to then find the cardinal directions or our position in space, the cardinal directions, the north, south, etc. And then we interpreted the word inexpensive as not having high-tech cameras or computers, etc. And then we also had to test for the accuracy of the optical compass, and then we had to check its performance at runtime. So this is the basic polarization pattern of the sky, and the lines over here in this figure, the lines are the direction of electric field. They are determined from the single Rayleigh scattering model. And if you can see over here the light is polarized, but over here it's not polarized. So the polarization of the light, for sun, it works like this, that the polarization is perpendicular to the direction of the rays. And then we had to build up a device to locate the sun. So this is a sort of optical compass that we built. This is the basic optical compass. You can see over here we borrowed the idea from another video of YouTube, the link for which is given below. So the advantage of this type of compass is that you can find the different polarization in a single compass, and you can then compare them. So okay, so here's a little video that I would like to share now. It's this one. So you can see over here, this is how the compass basically works. We have a screen in the background. The screen, it emits polarized light, and you can see over here how the polarization it changes. So okay, this was it. Now back to the slides. So this was the basic setup of our device to locate the sun. We looked at the patch of sky at a certain patch of sky, and we noticed its different theta and phi, which are spherical angles. And as you can see over here, this larger protector, it measures the phi direction, and this smaller protector where it measures the theta direction of the spherical coordinate system. And this is how we locate a position in any certain patch in the sky. And then we have also added a protector on this compass to notice how much rotation we have to do in order to find the polarization. So next is the finding the north. So the step one is that we pick a random match in the sky and we rotate the polarizer to the darkest or the brightest region, and then we note the angles of polarization, and then we repeat the above process for a different region of sky. And then we use a Lennard sphere, and we mark on the sphere the region of the sky using the curve protector, and the curve protector comes with the kit, and we draw the line at the angle of polarization. So this is a basic Lennard sphere. So if, for example, we have mentioned a patch of sky over here, and then we note down a patch of sky over here, and then we find different directions of polarization, and then we draw those directions. The step four is to draw the line of the polarization. We should have at least two such lines from two different patches of the sky, and the intersection of these lines, it will give the location of the sun in the sky. So for example, if we have this and where they intersect, that angle is where the sun is going to be, and then we mark it. So in this way we will get one position of sun in the sky, and then we repeat this process 1 to 4, all of the process 1 to 4 after 20 to 30 minutes, to get a different location of the sun in the sky. After that, I'll go into later. So after step 5, you will have two positions of the sun on the sphere, and then we extend both of these positions to get the trajectory of the sun in the sky, how the sun is moving in the sky. And then once you have the path line, the trajectory of the sun, you can draw a perpendicular like this. For example, you can draw a perpendicular bisector to it, and this will give you two options for north on the horizon. So if this is you draw a perpendicular bisector, which is the meridian, and on the horizon you will have two options. One is going to be north and one is going to be south, and depending on where you are, on which hemisphere you are, you can find out exactly which one is north and which one is south. Then you can determine north from the motion of the sun in the sky, and the sun moves from east to west. Okay, for the accuracy, we can check the accuracy of the device by comparing the results with the true north, and which can be determined from GPS or any other source. But the problem was that the device that we built, we left it we left it at our university when the lockdowns came into effect. So we were not able to test this. So our device is still in our hostel, so we were not able to actually compute the accuracy, but we built the device as we showed earlier. So this is the degree of polarization in the sky. Here you can have the sun over here or here, for example, and this is how this is at sunset or sunrise time, and this is how the degree of polarization would change. So you would have different accuracy results if you point the compass at different patches of the sky. For example, here you would have the highest accuracy. So the device under cloud cover. So this is a picture of a device under cloud cover. It did not work because the mean free path for a photon in a cloud is between 10 to 200 meter, but the usual thickness of cloud, it goes from 0.5 kilometer to 2 kilometer, which is much greater than the mean free path. So no polarization would be observable here. So the accuracy, it is going to depend on the size of the polarizer. Um, it is also going to be dependent on the number of divisions that we mark on the protector of the polarizer and the number of arms that we mark over there. And it would also depend on how the accuracies change with these parameters, and obviously increasing the divisions, increasing the arms would give a better contrast, and greater number of divisions means that you have to rotate it less. And a smaller size would means that you would have a patch in the sky. Now the errors which can arise that are that while rotating the polarizer for darkest or lightest shades, uh, there can arise some errors. Okay, and then errors can also arise when we transfer the angles on the globe to find our position, and then they can also arise when we are finding the trajectory. Now the ways to improve them are that instead of taking two readings of of the sun, we can take 3 to 5 readings to better pinpoint the sun. And instead of taking two solar positions, we can take more uh, for this, but to pinpoint the trajectory of sun in the sky. But then the waiting time would obviously increase. Now, and some other limitations are that the waiting time for the readings, it hinders its practicality, and you do not get exactly on spot readings. I mean, if you want to find out the cardinal directions, not the position of sun in the sky, for the cardinal directions you would have to wait, and under cloud cover our device, as we mentioned earlier, does not work. But you can find the patches in the sky which are not covered with clouds, and you can find the location of sun from there. Now further things which are interesting to look upon are the effect of wind on the accuracy of the compass, change of accuracy at different latitudes, altitudes, and the presence of different crystals which are present in the atmosphere. And also maybe find out how it works with some other sources of light, maybe a different planet, or using the moon as a light source, or polarization with a magnetic field, and testing it for different patches of the sky, and then noting actually quantifying the levels of polarization and testing it also during different times of the year. But because our device was left in the university, we were not able to look upon these things. So that is it for optical compass. Thank you.
Okay, good afternoon, dear audience. My name is Oleg Vashtenko, and I'm glad to present you our opposition on task number 9, Optical Compass. So according to the statement of the problem, the reporter should to investigate the phenomenon when the light falls on a Earth's surface and it appears polarized. So it was a task to design an inexpensive optical compass using this effect. Okay, the reporter starts his solution from the qualitative explanation of the effect, but in our opinion, this qualitative explanation was provided on a really not very good level because of, firstly, we didn't hear about this effect, why the sky becomes polarized. We think that it's really very important part of the report. After that, reporter said that her report will be divided on the parts. First part, it was interpretation of the task, and so we understand how reporter understand the statement of the problem, and after that, reporter demonstrate us the phenomenon, and she demonstrate to us experimental setup, but we can't understand is it her device or no. Reporter demonstrate us 3 different setups, and 2 of them wasn't her devices. So we think that it's really disadvantage of this report. I think that reporter should investigate and design her own device to obtain the experimental result. And also reporter using effect of the polarization of the sky to design her device. And in part of theoretical investigation, I want to say that there are really lack of the theoretical investigation of the following phenomenon. There are no qualitative explanation of the phenomenon, and it is very important that we didn't see any formulas or any prediction of this phenomenon. We even don't understand why the reporter trying to find the vector is perpendicular to the sun, why is this dark line appear. So then it's a time for experimental investigation. I think that many important parameters of the system were not investigated, and they're really very important that even in experimental part, we didn't see any values or any numbers. We think that in the statement of the problem, as a statement of the problem, reporter had to investigate the accuracy, but in her report, he said us about the parameter that influencing of the accuracy and precision of her device, but there are no any values, any percentage of these values, we think. So also I want to say that in her investigation, reporter used so much information from the open sources. Even the devices were not designed by her own. So in conclusion, I want to say that qualitative explanation was really lack. There was really lack of qualitative explanation, but there was clear experimental setup. We didn't see any theoretical investigation in this solution, and experimental verification of parameters in the task was too on a regular level, we think. So we want to propose such discussion topics, and I want to start the discussion now.
Thank you, dear opponent. I would like to ask you to write your name in our Zoom chat, and while you are writing your name, I will switch to discussion between reporter and opponent. Yep, you can start the discussion.
Okay, first question about show me please the system parameters that's affecting on the accuracy of your device.
And by the way, I post the IPT clock. You can, dear opponent and reporter, you can share your screen at the same time. I switched. You can not switch your sharing off, so we can see your both presentation at the same time. So please, you can continue.
Yes, hello. Can you please mention which question you want to answer? Hello?
Okay, yes, there is a question about the number of polarizators. Do you really state that is very important parameter, and what is the minimal number of polarizators we can use to obtain a nice result?
Okay. So these are the okay. So first, I'm going to answer this question. The as you can see over here that we have used 8 arms, and we have used more than 8 arms in this slide. The thing is that over here you can see a clear contrast between this part and this part. But if you use more arms, then you would not see a clear contrast between these points, but you would see a gradual change of polarization
Okay, but we can
it would
rotate
not.
such a device.
Yes, can you repeat it, please?
Yes, we can rotate such a device even if we have only 2 polarizators.
Exactly. You can rotate it, but this is just to give you a better contrast to see which one is the darkest and which one is the lightest. This is just to give you a better contrast. Okay, so do you have any other question, or do you want me to answer the question that you mentioned in
Okay,
your?
yes, I want to conclude that we may use only 2 polarizators, but using much number will be great. Yes, will be better.
Yes, but after a certain number, you will not be able to see the contrast like very
Okay,
good.
thank you. So, second question, I want you to try me to explain about why the sky polarizated.
Okay, so
In the
okay.
first part of your report, you showed us such a picture from the
Hmm.
article. Yes, but I can't understand using this. Why our sky is polarized?
Okay, so you mentioned presentation that we did not really uh, explain the model much. I accept that, but the thing is that we did not investigate this model because this model was already built up and it was present, so we just read it. The model is of Rayleigh scattering, and the Rayleigh scattering in the Rayleigh scattering, the particles they oscillate, and the light when it hits the particle, uh, when it hits those particle, it sort of uh, it changes its uh, the light is going to uh, it is going to change its polarization, not really change it, but only one type of polarization is going to be carried out in this collision.
Okay, thank
uh,
you. I really agree with your position, but I think it's maybe explained in the report. Okay, and the
yes,
second question
agreed with
about
that.
you said in your report that when the clouds in the sky, we
Hmm.
can't investigate this phenomenon, but we know that bees who
Hmm.
uses this effect even
Hmm.
fly there when there are many clouds. But
Hmm. Hmm.
what's the wrong in my logic?
Okay. So the thing is that we did find some studies which investigated this device which investigated the polarization under cloud cover, and the thing was that they use very sensitive equipment. So when the word inexpensive was used, so we just interpreted as being something that we could easily compute on our own. So that is why, like as you can see over here, with our compass and with our like naked eye experiments, we were not able to really find it. But but you can find you can navigate when some clouds are present. You can find the planet which is not covered with clouds, and then you can navigate it through that.
Okay, thank you. Also, in your report, you said that to find the north, we should make
Mm.
investigation during maybe 1 or 2 hours. But is there any information that we could know before the experiment to carry out the experiment during maybe 1 or 2 minutes?
Yes, yes. Okay, so if you know the path of the sun, so if you know the path of the sun in the sky at a certain date and at your certain latitude, then you can really pinpoint the path of the sun already in the sky, and then it is very easy to compute the cardinal directions from that. Like the thing that I mentioned over here uh, is only to sort of draw the path of the sun in the sky. But if you know it already, you will just have to put the values in there, and you have to just make an arc over there, and then you can easily find the cardinal direction from there.
So you can start the general discussion with the teams.
Okay,
Okay.
thank you. Could you please open the slide with the parameters affecting on the accuracy of your device?
Okay. So these are the different parameters which affect the accuracy, and then these are also the parameters where inaccuracy can arise, and then these are the things that we would have liked to investigate on how they affect the accuracy of the compass or the accuracy of the compass.
Okay, the opponent team has a question. We are interested in, like, you in your problem have to investigate the accuracy of the method. May you give a number of an accuracy, 10% or 5% or 3, and on which parameters does it depend?
Okay, so you are right. We did not actually experimentally investigate it. We just built the compass, and then we were not able to test it out. And I wanted to clarify one thing, that the devices I mentioned over here, these devices we built ourselves. The design of this design of the three arms, this we saw from a different source. But this all the compass that we have mentioned, that we have shown in the presentation, they are our own. This device, this we also built ourselves, as you can see over here. Then this thing, this Leonard sphere, this is a tool which is used for building spherical
Uh-huh. Okay,
trigonometry
okay.
models. This is
Thank
not
you.
the device.
Thank you. Could you show me, please, your experimental results
Okay,
once,
so
one time, only
okay,
once?
so I guess these are our experimental results. Sorry. Uh, do you want to draw something?
Uh, no, I didn't draw any. I want to ask
Hmm.
maybe the vector on the north in this picture and how it corresponds with the real north, because I see two pictures with many polarizators, and I can't understand where the north using these pictures even after your explanations. It's
Hmm.
really
Okay.
hard to me to find the position of the sun in my head and then make the theoretical investigation where will be north using such a device that you show but didn't use in your investigation. It's really very hard to me to understand.
Okay, Abul.
Okay, so basically what we do is it's a long process. I accept that first like there are too many steps. So first you have to take the polarization angles, as you can see in that the optical compass arm that we showed you, and then you transfer those angles on the Minard sphere. Basically, it acts like a dome in which inside which you are, and it depicts the sky. So sky. So you mark a point and then you trace, you use the protector and you mark the angle of insertion that you found. You draw that line on it, and then you make another line, and then the intersection is the point.
Thank you for your
Some other
explanation.
points, yeah.
Thank you for your explanation of the methodology of the experiment, but I still can't understand why you didn't made in your report. Okay, so
Okay, so we would like to discuss some things with you, if it's all right. Um, you said that this device, like many inaccuracies could arise in this device. Like, can you tell me ways in which we can improve this device?
I'm sorry, I can't understand your question, but we have no time now, and I think that we have really fruitful discussion on this point. We understand the qualitative explanation of the effects and the methodology of carrying the experiment. Thank you for your position.
Thank you so much.
Okay, may I ask a question? I would like to ask the reporter, is it principally possible to improve your device so it could be useful in cloudy day, or it is principally impossible?
Okay, so with our apparatus, with the filters that we used, we were not really able to okay,
Sorry, no
so we
sound.
were not really able to differentiate between different patches of the sky. Sorry. Can you hear me now?
Now, yes.
Okay, so with our particular device, with the filters that we made, we were not really able to differentiate the different degrees of polarization with our naked eye in this with this specific apparatus. But obviously, if we use computers and some better filters, maybe some more sensitive filters which are logged into computers, then in this way the device could be improved. And that
Okay,
would not
thank you.
really be inexpensive. I mean, you would have to do some calculations.
You intend to use ultraviolet part of light or not?
Sorry, can you please repeat that?
What filters do you intend to use?
Hello?
Uh, which filters, what kind of filters do
Okay,
you
what
intend to use?
filters do we intend to use? Okay, so maybe UV filters or infrared filters, we could investigate the phenomena with those filters and maybe see if they give us better results. And also the filters that we used in our device, we just took them out from an LCD screen because available where we live. So we had to
Okay,
improvise on that.
Okay, we have another question from the Lewis. Lewis, please, your question.
Thank you. For both the, the opponent and the reporter, can you think about or imagine how to improve or extend these devices in order to have to be useful in other planets? I mean, what will be the extension of what have to be the difference if you want to bring this device to other planets and to orientate yourselves there?
Okay, so
Okay, so we could possibly use the densities, how the molecules are in those atmosphere of other planets, and then accordingly we shift our theory from Rayleigh scattering and use much more May scattering and some other as well.
Yes, indeed. On other planets, if there exists an atmosphere, we can define the direction to the sun and thus to the north pole, for example, using the same scattering effect, but in this case, the scattering would be different. For example, in this problem, we can use the relay scattering, but in the other planets, the mis-scattering may be more important. And so we have to use another model to investigate. Yes, that's all.
Mm-hmm. Thank you for the answer. Now
Thank
we
you.
have now we have time for questions from Mikhail or Mark. If there is any, Mikhail, please.
I have one question to the opposition. So, do you have any proposal how to improve the setup that was proposed by the reporters? How could you improve the accuracy?
We think that mainly reporters have to more accurately define the lowest intensity line. It's a first improvement. Then using this, I don't know, more accurately define the direction to the sun and to the North Pole. Because of in the reporters' investigations, there was a problem because they have to, they need to have a difference in 2 hours, as I remember. But if we know our exact position and the exact time, we can define the North Pole more accurately. That's all.
Thank you. If there is no questions,
there is.
Yes,
Actually,
yes, there is. Okay,
okay,
yeah, here you are.
You have mentioned the source about cloud thickness and the length, the light path in that medium. So my question is, is it so that the very first collision of the photon makes it lose the information, the polarization completely? Or is it a relevant parameter, the distance, the average distance between scatterings, or is it more than that? Is my question clear?
I think yes, dear reporter.
Sorry, we did not understand the question. Could you repeat if there is time?
So does the photon immediately loses polarization after the very first collision with a water particle?
No, it does not in the first collision. It loses it after a bit more. Like you mentioned that the mean free path was 10 to 15, but I think, to my knowledge, it might lose after 3 to 4.
Thank you.